110, balanced binary tree. For this problem, a height of a balanced binary tree is defined as a binary tree in which the left and right subtrees of every node differ in height by no more than 1. And then so we can reuse our tree node code that we wrote the first stream. All right, what's the best way to go about doing this? Well, let's start off by creating a test case. 110 goes here. 110, there it goes. Balanced binary tree. Oops, setup's a little off there. Okay, this turns into a use, and that turns into that. And now we're going to try code action, right? We try to compile it, it's going to fail. We'll do code action and create the file, and then go to the file. Okay. Let's just copy this whole thing and just use the solution thing in here. I can just say pubstruct solution just to get that to build. Is balanced, we'll return false for now and see if it builds. Tree node, not in the scope. Okay, so we're going to add that. Create tree node. There. And then we're not using root. Okay, so now we'll write a test case. So example 1, we're going to write this test case here, test mod. Test example 1. We're going to say let tree is equal to tree node from vec bang, and then just this, and we change the nulls to the magic I32 min to build the tree, and then we're going to say is balanced. So in this case it's true. So we'll just say solution is balanced tree. And that should fail. Doesn't work. Why? Oh. Oh, because I need to pass in a reference. Got it. All right, so now we have a failing test case. And now we need to actually balance the tree. So how do we balance or how do we determine if a tree is balanced? I guess if the height of the left and the height of the right is the same. Oh. Or not the same, but within 1. So we can create a little height function. Which takes a root, and let's make this an option RC ref cell tree node. It's a little crazy. And this returns the height of the tree. So I guess we can do this. We can say left-hand side, left height is equal to self height of tree dot. We can't just do tree dot left. We have to tree borrow left, and then the right hand side is the height of the right, and then if let's say LH minus RH dot ABS is less than 2. Oh. Well, that's up here. How do we do this? And we can return the height of the tree, so it's just whichever one's bigger is the height of this subtree. But we have to return all the way up. Okay, let's change this. Let's change this to return an option, I32, and that way we can actually check the balance here. Right? That's where my brain was going with this. So if now we have to do this, match LHRH. Okay. If they're both sum, then we can check. And if they are balanced, then we can return lh.maxrh, whichever one's bigger, plus 1 for this branch of the tree. Else we'll return none. And for any other thing, if either one of them is none, then we'll return none. So will that work? It doesn't like this. Can't find value tree, right? Because I call it root, not tree. Oh, we have to destructure it. If let root sum root equals root. What do we do if this fails then? Else. We need an else condition here. If it's a none, then there's no height to it, so we just return sum 0. It's balanced. This should be ABS. Okay, so that I guess will return a height if the height of its subtrees are balanced. Otherwise, it'll return none, because that's all we care about, is whether or not the tree is balanced. So we'll call this height if balanced. And then up here, we just need to call it, right? If let sum root equals root, then return height if balance root is sum. If it's none, then it's balanced. So we can just return true. But that fails. Oh, I have to call it self. Height if balanced. Expected enum option. Oh, we don't have to destructure it this way. Right, because I already have that in there. So is that all we need to do? Height if balanced. All right, that test passes. If I can just do this, I could just... Oh, no, because I have to return bool, and I want to return option I32. Okay, so I can't just do that. Our next one is this, and this is a false. So let's see if this returns false. Oops. Didn't mean to do that. I meant to do that. Example 2. Let tree equals tree node from vec bang, paste. And again, these nulls need to be, oops, I32 min. And then we're going to assert not solution is balanced tree. All right. And that test passes. Good. And we have example 3. We're pass in an empty tree. And we'll say it is balanced. Solution is balanced none. And that passes. I'm looking here to see whether all the tests pass. Okay, that means we can submit this as a possible solution for our problem. Just, oops, I pasted too much. There. Submit. Look at that. It ran in 0 milliseconds. I don't trust these runtime numbers anymore after we played around with it the other day. Okay, so that's that solution done. All we care about is whether or not the tree left and right side is less than 2 difference in height. And as soon as we find a subtree that's more than, or 2 or more, then we just start returning none, and then that none bubbles all the way to the top. So that's pretty good. Git status, git add source. Oops. git add source, git commit -m, problem 110, balanced binary tree. All right, that went really, really fast.